Finally, it's my pleasure to introduce Ann Matsuura, the Director of Quantum Applications and Architecture at Intel. Dr. Matsuura has been a strategic investor in technology startups at In-Q-Tel, a funder of Basic Science at the Air Force Office of Scientific Research, and has experience as a science policymaker as a special assistant to the U.S. Deputy Undersecretary of Defense for Laboratories and Basic Science. Please give Ann a warm welcome.
Thank you for that kind introduction. So, when I moved to Intel 8 years ago, I felt like a fish out of water. And that's because I was trained as an experimental condensed matter physicist, but I didn't get hired into the Intel fabrication facility where all of the materials physics and the condensed matter physics takes place. Instead, I was hired into Intel Labs, where all of this computer engineering research and architectural design research is really what Intel Labs does. About that time, Intel jumped into the quantum computing arena, and we had to make this decision on how could we best contribute to the quantum computing research field. I mean, there are already many big players, lots of startups, many universities doing great research and contributing to the quantum computing field. So what could Intel do? And what we decided, I think, was a very good decision. We decided that we should leverage what we do best, and that is we know how to build classical computing systems. Since that time, I've noticed that the quantum computing research area, that there are more physicists who are also open to looking at engineering and computer engineering techniques to help the quantum computing research effort. And I think that's really important. And so I want to talk a little bit today about what quantum can learn from classical computing, and a little bit about my experience at Intel. Okay, so how can quantum computing learn from classical computing? After all, quantum computing is an entirely new kind of compute, a paradigm shift, entirely different programming model. It's entirely different from classical. So how can we learn from classical? Well, at the end of the day, what we want to do is create a scalable, reliable, user-friendly, practical, commercial-sized quantum computational system. And classical computer architects have had decades of experience creating a reliable, practical, user-friendly, scalable, commercial-sized, classical computational systems. So I think there is a lot we can learn from the techniques, their experience, and the pitfalls that they've run into. And I think that learning from them can help us to guide our quantum architecture research. And I think I'm probably speaking to the choir, because I know University of Chicago has a fantastic quantum architecture program. So up until this point, we've kind of been influenced, as many new technologies are, by, this is an old baseball movie, hopefully some of you know it, Field of Dreams, right? Where we say, if you build it, they will come and use it. You know, that's really, in my experience, that's really not true for new technologies. And there's no reason why it should be true for quantum either. Usually for new technologies, you have a small subset of really excited early adopters who will walk through fire in order to learn what they have to learn, do what they have to do in order to use this cool new technology. But if we really want a new technology to take hold, we have to widen that user base. And in order to do that, we have to make it more user-friendly. We have to make it more accessible to non-quantum experts. And classical computer architects have experience with this. Back in the day, who would have thought that classical computers would be anything but a niche technology? Who would have thought we'd be wearing them on our wrists, they'd be carrying them in our bags, that they'd be so ubiquitous that we wouldn't be able to imagine life without classical computational systems? So I think there's also a lot we can learn from classical architects in this respect. So we really need to be thinking about intentionally, how do we move quantum computing out of the physics lab and into a more user-friendly technology, and how can classical computing techniques help us? So I'd like to talk a little bit today about examples from hardware, software, also I think really importantly, system architecture. I think that we need to, it doesn't matter how great your hardware is or how great your software is, if the whole computational system doesn't perform well as a full computational one unit, a whole computational system performing together, full system performance, then it's really not a performant computer. So I'll talk a little bit about all of these spaces today and some of my experience at Intel. So let's start on the hardware side. So quantum hardware certainly can learn from and leverage classical computing. For us, what that means is we chose a type of qubit. We chose silicon quantum dot qubits because they look like one-electron transistors. And this is our fabrication facility in Oregon. It is where we fabricate our classical computer chips. It's also where we fabricate our qubit chips. We have a 300 millimeter process node dedicated for manufacturing qubit chips. And they look a lot, the silicon quantum dot qubits look a lot like one-electron transistors. If you look at this picture on the right, it's a cartoon of our qubit chip. The left, cartoon of a transistor. You can see the similarities. One of the main differences is we have to fabricate more gates in order to control the potential landscape, in order to interact electrons when and where we want to. And the other big main difference, I think, is that we use isotopically purified silicon-28 to eliminate nuclear spins. But at the end of the day, our qubit device is a scaled, gated electrostatic device, and so it's perfect for our manufacturing capabilities. On a single wafer, we can fabricate more than 10,000 quantum devices. And since, because of our tight process control, those devices have very little variability between them. And so we're able to use statistical data from these many devices and learn to make a better process, to make better qubit devices, exactly like we do for transistor technologies. And we've also been able to leverage our wafer-level testing capability. So we partnered with Bluefors and A4 to combine a wafer-level e-test prober with a cryogenic refrigerator, because our qubits are cryogenic. And we got this cryogenic cryoprober here, which is also in our manufacturing plant in Oregon. And here we can now do wafer-level testing of the devices at 1 Kelvin. This has sped up our testing capability by orders of magnitude. So now we have this really nice research and development pipeline for manufacturing our qubit chips, and we have a feedback loop, right? We can test them rapidly and so we have a R&D pipeline and feedback. And so this is exactly like we like to do for transistor technologies. The other thing we're doing is we're leveraging our CMOS technology. We have cryogenic qubit control chips. And so the idea behind this is we're trying to bring what is usually room temperature control electronics into the refrigerator to be at cryogenic temperatures near our qubits. And the idea then is that we can reduce some of the input-output wires going from room temperature electronics into the cryogenic refrigerator. This is kind of to help us hopefully scale up the numbers of qubits more easily. So for this, we've leveraged our integrated circuit design expertise, our RF, analog, and digital design. We've also leveraged our 22 nanometer FinFET technology. We're able to create the process infrastructure for cryogenic libraries, cryogenic models for these types of chips. And so here we've leveraged our CMOS technology. There's also a lot we can learn on the software side, on the software engineering, software design side of things. For instance, one example is we've used classical compiler design for our quantum compiler. We've based our quantum compiler on LLVM, an industry standard, extended it with quantum extensions. Here you can see our quantum compiler targets a binary quantum instruction set. We have a quantum runtime that manages the execution of the quantum program. Users can define operations. They get decomposed into operations that are available on our quantum dot chips. We also have new ways of representing operations, which have enabled a larger number of algorithm optimization compiler passes. This is interesting because we can actually, in our compiler, you can compare compiler files, just like you can in a classical compiler, and you can see how your algorithm is being optimized. The other nice thing about using LLVM IR is that we will be able to open source the front end of the compiler to allow developers to contribute new compiler passes and also to use whatever front-end technologies that they desire. I also wanted to talk about programming a quantum computer a little bit too, because I think this is so important. And there has been work going on in this area, but this is a hard problem to solve. And so I think there is something that we can learn from classical design here as well. I suspect everyone here is familiar. This is a quantum algorithm, but just in case someone in the Zoom world is not, this is a 5-qubit algorithm. Each line represents a qubit. As you go from left to right, you're seeing all the operations that happen to the qubit. So you'll notice there's like Rx, which is a single qubit rotation around the x-axis, right? Or you have these little vertical lines, which are 2-qubit operations, controlled knot operations. This is not obvious to program if you don't know quantum computing. And I think that we need to start thinking more seriously about how do you abstract away the needing to know so much about quantum hardware. I think we need that in order to get that larger user base that we talked about earlier. And classical computer engineers have done this in classical systems years ago. I also think we can learn from classical system architecture design. Now, I think this is actually really important. Again, it doesn't matter how fantastic your hardware is or how fantastic your software is. It's got to work together as one unit. Otherwise, you don't get system performance. And in the classical world, you always hear algorithm developers always want to know, how well is my algorithm going to perform on this computational system versus that one? We need these sorts of algorithm system performance metrics. System performance depends on thinking about architectural design trade-offs. And this is the way a classical computer architect would think, right? If you tweak something in one part of the computational stack, it affects something in another part. This is a diagram from a paper I wrote a number of years ago, so it's a little old, but the concept is still the same. You change one part of the puzzle, it's going to affect the shape of other parts of the puzzle. And I think that's something we really need to keep in mind as we're working on hardware and software, that we need to be thinking about how does it all hang together, system. Also, full system and simulation can help us not only to develop the system architecture, but it's also, you can design a lot in simulation before you build or before you tweak your hardware. There's a lot to learn from classical computer engineers here as well, because they have all kinds of simulators, behavioral models, all of this. And being able to do more and more in simulation like they do, I think can help us speed up accelerate some of our progress. Also, it's less costly if you're talking about building hardware. And so, I'm hearing more and more people, quantum researchers, talk about co-design. I just wanted to point out, what we mean by co-design. So there are things like workload-driven co-design, right, where you actually run a small algorithm, a small workload from a useful application area. It can be very small, right? You run it full stack to real qubits, and you can understand what functionalities the system architecture has to provide in order to run the algorithm efficiently and accurately on real qubits. It's like this is the way a classical computer architect would think. On the other side, of course, going upwards, the hardware constraints affect the design of your system architecture. It affects the way you develop your software. Now, these are results from work we did with the Technical University of Delft in the Netherlands. We did some workload-driven co-design work that led to a new instruction. And this is actually what I would consider as a workload from what I would consider the materials design application. It was modeling materials in simulation. It's actually a many-body localization problem. And for those, I think everyone's familiar, but if you're not, these are block spheres. The red vector represents a qubit, and so you're seeing a rotation around the y-axis and a rotation around the z-axis on the left here. And that's how we were doing our rotations. We ended up having to rotate our qubits to angles that were not on any of the axes. So we do like on the left. We would rotate around y, rotate around z. And so the obvious thing was, hey, let's put in a new instruction into our instruction set and go straight there and rotate around a different axis. This sped up the execution of the algorithm by about, not surprisingly, by about 2x. But that's a way where workload-driven co-design actually changed our instruction set or augmented our instruction set. Another example of workload-driven co-design, this was with the quantum Fourier transform, very common workload. And here we ran in simulation the QFT on a line of qubits, on a ladder of qubits, and a two-dimensional grid of qubits. And our qubit chip team was always saying, well, it's really easy for us to manufacture a line, but it's really hard for us to manufacture a two-dimensional grid, a square grid. And so what we found was on the right, the blue data is from the ladder, the red data from the two-dimensional grid. We found that the ladder-based connectivity qubits actually QFT performed nearly as well as on a two-dimensional grid. And what our qubit team took away from this is, hey, maybe for small numbers of qubits, maybe a a ladder-based structure is good enough for these qubit research chips. And so so workload-driven co-design affected the qubit connectivity design of our chips. Now, I wanted to end with something that I'm starting to work on right now with a classical parallel computing designer at Intel Labs. And his name is Tim Madsen, and he actually was the innovator of what they call parallel research kernels. This is for classical parallel computational systems. And what these are, they're basically design tools. If a parallel computing system can run all of the simple kernels that are represented on the right-hand side, that's a complete set of all the kinds of functionalities that these many, many application areas need in order to run workloads from their application areas. So Tim had gone out to application developers in the classical parallel world and had found out for all these different application areas, what are the functions basically that they would need, the system would need to be able to compute in order to run workloads from their application area. Then he distilled them down to the simplest possible kernel, or more like a pattern. And he found that these are the PRK. Basically, if a parallel computational system can perform all of those kernels well, then you have a highly performant classical parallel computing system. And what I'm interested in with Tim is, can we start doing the same thing with quantum research kernels? And Tim and I have written a very short, very easy to read little paper on arXiv where we started to sketch out 3 potential quantum research kernels. But we need help from people in the audience. We would like to talk to a lot of application developers, quantum application developers from all areas, not just materials and chemistry, but also finance, machine learning, traveling salesmen, logistics, cryptography, climate modeling, any application area that you're working on. And we would like to know what your algorithms look like. What does the quantum computer have to do? And we will be holding a virtual workshop sometime first half of next year. So stay tuned, because we would love input and participation from you. The workshop will be advertised on the Intel Labs LinkedIn page, or if you know me or have my address, just contact me. So we're very eager to get this started. I think it sounds like fun, and it'll be a nice way to collaborate. And I think it's an important thing, too, if we can help us to design a performant quantum computer, if we know what functionalities it needs to provide. So thank you very much for your time. I will take questions.
Thank you very much, Anne. And let me briefly introduce Professor Mark Saffman from the University of Wisconsin-Madison, a leader in cold atom quantum computing, who's going to moderate this session. Mark?
Thanks, David. Thank you, Anne, for that great talk. We can take questions now, please. Yeah, I can probably just give you this one, yeah.
Thanks for the wonderful talk. My question was, what mistakes from classical computing can we learn from that we don't want to repeat for quantum?
Wow, so you're asking the experimental physicist this. So I put that in there, and I probably shouldn't have. I guess I already talked to a classical computer expert. They would probably say we made no mistakes. But I'm sure there have to be. Knowing technologies in general, the advancement of technologies. There have to be not only design techniques that we want to emulate, but there have to also be things we do not emulate. I don't know if anyone here, I know there are classical computer architects in the room, so if anyone has a answer for that, I'd welcome that answer as well. Got some hands.
Seems not. Let's take another question at the back there on the
Or
left.
someone may have an answer for him.
Hi. My question concerns the connection and the transfer of data between classical and quantum computers. For some time, at least in the materials and quantum chemistry arena, while solving problem on quantum computer, we will do many calculation on classical computer and some on quantum computers. And I would be interested to know your opinion on the challenges about this transfer.
That's a very good question. I also think for quantum error correction, we're going to actually need a really tight coupling between classical and quantum computers. So it's an area that's starting to, what would a quantum machine look like sitting at an HPC center, for instance? There are starting to be little workshops, little panels talking about that. I've been asked to talk on those quite often, and I tell you, I ask a ton of questions and I don't answer many. This is an area of architecture that I think that for some of you who are just starting your careers, it's actually going to be a very interesting thing. What does that look like? How do we? I personally think we have to place the quantum machine at an HPC center, right? To shorten the latency for QEC, not only for variational algorithms in general.
Let's take another question here in the middle.
Hey, thanks for the talk. So I was curious, it's great to see a software stack that's being designed with inspiration from classical software stacks and like the compiler pipeline. I'm curious whether the compiler pipeline you're developing, whether it's specific to the hardware architecture that Intel's working on, or whether there are sort of like plug and play pieces where you might imagine where you can use the same stack, but then plug in a different architecture, a different gate set, and still have a functional compilation stack?
That's a very good question. So we are fashioning our stack for our quantum dot qubits. However, the quantum dot qubits are still, constantly in research as well, constantly changing. So we have had to make the stack a bit flexible. And the thought that you have raised has come up a number of times. I'm trying hard to make sure that we don't fashion a stack that is difficult to change to be able to work with other kinds of qubits. That's something that's come up a lot recently. So hopefully it's a change of the instruction set, right? And a little bit more than that, but hopefully it's not too onerous to be able to change.
Thank you.
And I'd like to interject a hardware-related question. You're at the Chicago Quantum Exchange today, and the CQE is doing many things, but it's also really a hotbed of research on quantum networking. Could you comment on how Intel views the importance or roadmap for connecting networking to your silicon processors?
Yeah, we have not talked that much about that. That's, we are still focused. We have probably chosen one of the least mature qubit types because we think if anyone's going to be able to make quantum dot qubits work, it's Intel, right? Because they look so darn much like transistors, right? But so we think about things like, photonic networking and this sort of thing, but we haven't really focused our efforts on how do you network more computers together. Our actual hope is that we'll be able to put more qubits. They're very small, right? They're basically like single electrons, that we're going to be able to put more qubits on a chip. As a physicist, I also sort of realize there may be all kinds of physics challenges when we start to put them so close together. But anyways, that's our hope for now.
Okay, thank you. Another question at the back there?
Hi. Okay, so another hardware question, actually. So this goes back to earlier in the presentation. So for, say, CMOS design, we typically use these electronic design automation tools, right?
Yes.
Is there, are you thinking about quantum design automation tools there, like in order to, like help with the layout of the 10,000 qubits, how that would come about? Like the models for the individual devices there, and so yeah, that's the question.
Yeah, still pretty early stage for that too, but that is a very interesting point. At this point, it really is still, my team doing research in conjunction with the Qubit chip team and trying to understand how these workloads actually work on different kinds of layouts. But yeah, this is, and they're small workloads at this point, right? But that is something that also has come up. We haven't addressed it yet.
Any final questions? One more over there.
So I was happy to see there was one slide where you talked a little bit about LLVM and your, your compilation process.
Yes.
I know there's a big effort going on called the QIR Alliance, where a lot of different players in quantum computing are trying to, create an LLVM, common intermediate representation that can target different machines. I was wondering if Intel is playing a role in that, or if you're working on something in parallel.
We have not played a role in that. So this was we've been working on this a long time. So this did come up in parallel.
But you're trying to do something similar to create an IR that in principle would be able to target many different.
That's correct.
All right. Cool. Thanks.
We still have time for more questions if there are. Yes, here.
So Intel has probably the best semiconductor technology anywhere. For your hardware research, do you now focus on making your qubits as error, reducing the error? Or where are you with scaling? Do you think you have now something which you could scale to hundreds or thousands of qubits?
We are still worried a lot about reliability, as I think is not surprising considering that it's, again, one of the least mature qubit types that we've chosen. But we constantly are thinking about scaling, though, as well. So, if that answers your question.
What is the main obstacle?
Probably, I'm not the hardware side, so I'm just going to be opining, right? From my perspective, it's always probably going to be reliability, right?
I think we're going to have to move on to the next speaker. We can take further questions offline, but let's thank Anne again for an inspiring talk.